Okay, good afternoon, everyone. Let me very briefly review what we did last time. We discussed the origins of band gap in one-dimensional photonic crystal, one-dimensional distributed Bragg reflector. And one of the last things that we did was this band diagram for a structure, which in this case would be periodic with periodicity A. We discussed how when you tune periodic perturbation inside of the structure, these band gaps would occur at the high symmetry points of the structure. So if you remove all the periodic perturbation and go back to a uniform material with refractive index, which is equal to the average refractive index of the structure, then your dispersion omega k relation for photons propagating through the structure would follow kind of green straight line. But then when you introduce perturbation, as you introduce first harmonic in the electric constant, which is of course periodic function, then you would open this first order band gap at pi over a, and then second order band gap, third order band gap. And they are mostly proportional to first, second, third order, third harmonics in the expansion of the dielectric constant. And then we also know that each point inside of this band diagram would correspond to block states, one-dimensional block states in this particular case. Knowing the properties of the block states, we actually know that they are periodic in K-space with the periodicity of the Brillouin zone. So all the block states inside of the first Brillouin zone, which are here from minus pi over a to plus pi over a, would be periodically repeated. And then that leads to periodicity of the band diagram. And we also know that we have a symmetry relative to k equal to 0 point. So once you build up this band diagram around the green line and knowing the periodicity of the block states, you can actually map it back into the first Brillouin zone from all of that, because there is a periodicity with n times 2 pi over a, and then there is also symmetry relative to k equal to 0. So that's so-called unfolded band diagram, and then you can also draw it in the folded band scheme back inside of the first Brillouin zone. And the other thing that we started at the very end of the class last time was this discussion of the dielectric and air bands. How do block states differ inside of different points of the band diagram, because they have periodicity that is dictated by periodicity of the structure and also by k point that they correspond to. So in this particular case, we were looking into block states corresponding to k equal to pi over a point, which is the edge of the Brillouin zone. And we know that block states are expressed as one-dimensional block states in this particular case. But the question was, how do the block states that are at different frequencies differ from each other? And we started slowly introducing this concept of dielectric and air bands, because we said that the difference between the field patterns would be in where electric field energy density is concentrated. So for the dielectric band, it would be in the regions of higher refractive index, and for the air band in the regions of lower refractive index. But we didn't really complete that discussion. We just discussed it from kind of a very simple picture, where we neglected the overlap of the field with anything other than high or low index region. And we said, well, when we had the same spatial field pattern for the two block states, and in this particular case, it's determined by the periodicity, the one that is inside of the higher index region would have to have a lower frequency and vice versa. But of course, this is a very crude approximation. So at the very end of the class, we said that today we would talk about so-called electromagnetic variational theorem, which gives you a little bit more information about how these different block modes would look like. So it's not only that for the first order band gap, this lower frequency band would have electric field energy density primarily in the high index region as plotted here, and for the air band inside of the low index region. But from this electromagnetic variational theorem, you can also infer how the even higher order bands would look like. And you remember that there is another band here that would be folded and would be at higher frequency. So the question is how that band would look like, since you know that it has exactly the same periodicity as the bottom two, and that would be periodicity of 2 times a in this particular case, coming from pi over a. Okay, so any questions about this before we move forward, or everybody is on board? All right. Okay, so let's now go into electromagnetic variational theory. Okay, so we will introduce it here following initially at least the discussion from photonic crystals by John Apples and Johnson. It's actually very simple. We just start from Maxwell's equations, right? Curl equations, and we combine them into wave equation, and we'll combine them into wave equation for magnetic field because you can directly obtain it in the so-called Hermitian form. We'll have more discussion of that in about a week or two when we start talking about normal mode expansion inside of materials with variation of the electric constant, and this concept of putting wave equation into a Hermitian form so that you obtain orthogonal modes will be important, and we'll see how we can do that for electric field. But for now, we'll just do it for magnetic field, and you have to kind of take it for granted that it is in Hermitian form. So what does that mean, right? So let's start from curl equations for the system. So this is the one for magnetic field, this is the one for electric field, and epsilon is the dielectric constant distribution. And of course, we're talking about photonic crystals here, so epsilon would be periodic, but this is also true in general. It doesn't have to be a periodic. I mean, what we're discussing now would hold for other distributions of epsilon. We will just divide the first equation with epsilon here and take curl again. So obviously you'll have curl of 1 over epsilon, curl of h, and then on the right-hand side, you will have something proportional to curl of E, and then you can replace that with the expression that depends on H from the other Maxwell's equation. So you basically just obtain the wave equation for magnetic field. Okay, and I'm sure you've seen this before. This is a very simple procedure for constructing the wave equation. Here, what is interesting is that you can show that this particular equation is Hermitian. I mean, if you express it as the eigenvalue equation for some operator, and you label that operator with theta. So theta h is omega squared mu naught h, right? So what's theta? Theta would be curl of 1 over epsilon curl, right? Of that operator is Hermitian operator. So what does Hermitian operator mean? Hermitian operator means that for any two, in this case, vector fields, because it's an operator that acts on a vector field, and let's label them as f and g. If you construct inner product between g and theta f, that would be the same as when the operator jumps to the first function of the inner product, theta g f, right? So that's the definition of the Hermitian operator. So what is the inner product? Inner product is defined as the integral over the whole space of the first function, complex conjugate, times the second function, and this is of course integrated over the whole space. So g theta f would be the same as g complex conjugate product with theta f, right? So this is this operator acting on function f, and if the operator is Hermitian, then this has to be the same as theta g complex conjugate f integrated over the whole space. And we will not really prove that this is the case for theta, although it's pretty simple to prove. You can do it by integration by parts. And when you look at the operator itself, you see that the operator is symmetric, right? So when you have something like g and then curl of 1 over epsilon curl of f, you will slowly, I mean, curl is kind of differentiation, right? So when you're doing integration by part, you will be moving that differentiation or curl from one function to another. So as you are doing that in steps, in the first step, you will have something like curl of g and then 1 over epsilon multiplying all of that and then curl of f, and then you have to move another curl. So as you're slowly moving curl, you will end up with curl of 1 over epsilon curl of g, right? And this symmetry in this operator is also what is going to help you to prove that it is Hermitian. You will see that if you construct the same thing for electric field, there will be issues with the operator of curl of E not being directly, actually 1 over epsilon curl of curl not being actually Hermitian operator. So we'll do something to tweak it to make it kind of more symmetric and make it in the Hermitian form. So that will happen in about 2 weeks. But for now, actually this particular operator is Hermitian. This can be proven. And now the question is, why does that help us? So what do we know about eigenstates and eigenvalues of Hermitian operators? Anybody? I'm sure you've heard that before. Yeah, Jason?
They're real?
Yes, yes. So eigenvalues are real. And what about the eigenvectors or eigenfunctions? The ones that correspond to different eigenvalues have to be orthogonal to each other, right? So that's all good, right? Because real eigenvalues, what are the eigenvalues of the operator theta? It's omega squared mu naught, right? So we know that these are real, right? So that's all good because frequencies are frequencies of the electromagnetic field. And also eigenstates or eigenfunctions that correspond to different eigenvalues, right, are automatically orthogonal. And this is exactly why we will go through the effort to put every eigenvalue equation into Hermitian form for normal mode expansion. So we'll do that for electric field, because if you know that electric field distributions corresponding to different frequencies, let's say, are automatically orthogonal, that is going to help you construct the basis for field expansion. And also when you do quantization, you right away end up with decoupled harmonic oscillators, right? So we will always try to start with a Hermitian operator if we can, right? But for now, we know that theta is Hermitian, so we know eigenvalues, which means frequencies, will have to be real, and also eigenfunctions that correspond to different eigenvalues have to be orthogonal, which means magnetic field patterns corresponding to different omegas will have to be orthogonal to each other, okay? And that's good, right? So orthogonal as defined by this inner product. Okay, so let's go back, right, to our eigenvalue equation and look into this a little bit more. So what we will do is first we will denote energy as W, right? And let's assume that the system is lossless, right? So if the system is lossless, you know that energy will oscillate in time with frequency 2 omega between electric and magnetic field energy, and total energy will stay constant. It's kind of like kinetic and potential energy, like a harmonic oscillator. So the total energy would be double of the magnetic field energy, and you can calculate it here, right? So that's W, but you can also calculate it equally from electric field. So what we will do is we will multiply, we will calculate the inner product between magnetic field and theta, this operator applied to the magnetic field, okay? So what is inner product between H and theta H? Theta H would be basically this, like left side of the whole equation. And you can actually go through this whole expression and rearrange it. But H and theta H also from the right-hand side of the equation, or by multiplying both sides of the equation with H on the right-hand side of the equation, you will obtain something that's proportional to the energy, right? So that's like just the wave equation that you have here, right? So multiply both sides of the wave equation with H and integrate over the whole space. On the left-hand side, you have H theta H. On the right-hand side, you will have basically omega squared mu naught, and then inner product of H and H over the whole space, which gives you energy, right? So this whole thing is energy. Okay, so what we will do now is we will just divide both sides of the equation with energy, right? And you can right away express that omega squared mu naught is H theta H divided by inner product between H and H, or you can write that omega squared is H theta H divided by energy. It's a very simple exercise. I mean, if you have any questions, let me know. But since it's very simple, we'll just follow the derivation on the slide instead of writing it again. There is nothing new here. We just wrote it as expression, right? So here we have frequency, and that frequency is equal to this inner product between magnetic field and theta H divided by energy, which you can calculate as mu and HH. So if you took quantum mechanics, you probably had a lecture on variational method in quantum mechanics, which you use when you don't really know how eigenfunctions of the system look like, right? But it helps you find the eigenfunctions of the system. So if you, for example, here have this expression that defines frequency, right? And you look at this expression and you don't know how magnetic field pattern for the particular problem looks like, how would you be able to find magnetic field pattern corresponding to lowest frequency state, eigenmode of the system, right? So how would you do that? Well, in variational principle, in variational method, what you would do is you would plug in some magnetic field calculate the expression on the right-hand side. You guess some magnetic field, you plug in, into the expression on the right-hand side, and then you change that magnetic field until you minimize omega, right? Because you know that the lowest frequency mode has to minimize this particular expression. Does that make sense? Right? So, I mean, of course, if you have other ways of calculating magnetic field, you will plug it in here and you calculate frequency from this expression. But if you don't know how magnetic field looks like, you know that magnetic field for the lowest frequency mode would be the one that would minimize this expression, okay? So then how does the next eigenmode look like, right? Once you plug in and massage that magnetic field and find the one that minimizes the expression, how do you find the magnetic field for the next higher frequency eigenmode of the system? You have to repeat the same process, but you have to find magnetic field that again minimizes this expression, but it minimizes it in the eigen subspace that is orthogonal to the lowest frequency mode that you already found, right? Because this is a Hermitian operator and all of the eigenmodes have to be orthogonal to each other if they correspond to different frequencies. Does that make sense? And we're not really solving here for the field. We're just using this observation to conclude something about the field patterns for different block states. Yeah, you should.
From my understanding of quantum mechanics, in the variation principle, you try to guess some wave function, and then those wave function will tell you what's the minimum energy state, but you have no idea on is that the true ground state or not.
Yes, but you are just guessing until you find something that would minimize the ground state. Yes, so that's exactly the point here, right? But we're not really solving for that. We're just saying whatever that ground state eigenfunction magnetic field is, lowest eigen frequency ground state, lowest frequency eigenmode of the system is, it would be minimizing this, right?
Usually it's pretty hard to find the eigenstates that you're trying to find.
Yes, but we don't, in this particular case, we don't even have to find it. You'll see in a moment why we're doing this. The only thing that you need to remember is whatever that eigenstate is, it would minimize this. And we'll see what the consequences of that are on the pattern of the field. That's all that we want to learn from this exercise, okay? Because remember, we're going through this in order to explain what the frequency between patterns of the field would look at the same K point in the band diagram, but in different bands, okay? So whatever the lowest frequency eigenmode of the system is, it would minimize this. And then the next mode would also minimize this, but in the eigen subspace that's orthogonal to the space of the previous mode that you already found, okay? That's all, right? So that's what we're doing, right? And of course you can do that for magnetic field, but we will convert this into expressions for electric field, because when we just rewrite this whole thing with the expressions for electric field, it would give us information about the electric field, right? Because we're discussing electric field pattern, and we discussed that previously in the band diagram, and we plotted the electric field pattern. So we'll just do that again, right? So just go back to this functional that we are minimizing, right? So it's calculated as h theta h divided by energy. Energy, of course, can be expressed either from the electric field or from magnetic field. This would be the expression for energy expressed in terms of the electric field. Of course, again, assuming that system is lossless, right? So there is equal energy in electric and magnetic field. And then h theta h, if you write it as the actual integral, because this is just the inner product, it's h complex conjugate, and then this is theta h is just this whole functional, or the left side of the wave equation. And then you can use Maxwell's equations to express this in terms of the electric field, right? So 1 over epsilon curl of h, that's proportional to electric field times some frequency, and then curl of that would be is also proportional to h, right? So that this h here we can express as curl of E, and this whole thing here we can express as curl of E as well, okay? So we will have curl of E twice with complex conjugate, or we'll have basically magnitude squared of curl of E, right? So this whole expression here, when you calculate it, would be proportional also to this. You can calculate it from the integral of electric field, and the denominator is proportional to energy, which you can also calculate from electric field. So rewriting this functional that we are minimizing, it is basically equal to this particular expression. So it depends on the integral of magnitude of curl of E over the whole space, and then you have the energy in electric field. So now just going back again to the same exercise, right? I mean, what we, or not exercise, but the conclusion that we had. Imagine that you really don't know how electric field of your eigenmodes of the system looks like. How do they actually look like? How do electric field patterns of the system look like, right? So we know, again, that from the variational method in quantum mechanics, I mean, to find the electric field pattern for the lowest frequency mode, you will have to guess and massage electric field until you find the electric field pattern, some function, E, that would minimize this whole expression, right? So when would that happen, right? So if you look at this expression, numerator is proportional to curl of E squared, and the denominator is proportional to integral of epsilon E squared, right? So if you have no idea how electric field solution for the system looks like, right? But you just have epsilon distribution for the system, what would you do, right? So what would you do to minimize this? Well, you would pick E, which is maximum in the points where also epsilon is maximum. You agree with me? Because if you pick E to be maximum where epsilon is minimum, then this whole denominator is not going to be maximized, okay? So just by guessing, if I want to minimize this, I will put E where epsilon is strong, right, for the lowest frequency eigenstate. And what about the numerator? Well, we have curl of E here, right? And curl of E is just more sophisticated version of the derivative, right? I mean, it's just three-dimensional combination of derivatives, partial derivatives in 3 dimensions. So how do you minimize derivatives of the field? You need to have, I mean, you minimize it if it's constant, right? But in other words, you want to minimize the number of, minimize variations in the electric field patterns. If electric field is smooth, if it has minimum number of oscillations, then this whole thing would be minimized.
Right, so
you agree with me?
I don't completely get, so if we're trying to minimize this, why do we not just set the curl to be 0 and solve for that?
I mean, that would definitely be minimum, but that would be omega equal to 0, right? So it's not really AC solution for the field, right? So it's, if you want to look at the fields that are having particular oscillating frequency, that would be a trivial solution, right? So for non-zero frequency, you still don't want to have E equal to 0, but you want to minimize number of oscillations in the field, which means kind of smooth change in the field pattern, okay? Does that make sense? Right. So now, you know, that kind of tells you how the lowest eigenfrequency mode should look like, right? It will have electric field concentrating in the regions of higher epsilon, right? And now let's go back to our periodic structure, which has high and low index regions, right? So if you want to minimize this, you would have to put electric field maximum of E squared in the regions where epsilon is strong, and you would also like to minimize number of oscillations in electric field in order to minimize the curl on electric field, right? So that's exactly what we discussed if the electric band would be, right? Which concentrates electric field in the regions of high epsilon, right? So that comes from the denominator here. And then also for the first two bands, you also have minimum number of oscillations in the field. This other conclusion that we have will tell you how electric field patterns would look even for a higher order bands that you have in the band diagram. So going back to our discussion and this plot that we took from Giannopoulos' book, let's use our conclusions, right, to explain what's going on here. So we have two block states that correspond to same point in the band diagram, pi over a, right? We know that each block state is a product of something that's periodic with periodicity of the lattice. So it has periodicity of a, but then k equal to pi over a gives you additional periodicity of 2a, right? So both of these block states have to be periodic with periodicity block 2a, right? And this is, of course, drawing, right? But you are expecting the one at lower frequency to have maxima of and minima of electric field, or or basically points with the strongest amplitude of electric field inside of the high index region. And that's indeed happening, right? So that's the dielectric band. So this dielectric band would have points where magnitude of E is strong, overlapping with high index region, which is blue. And the other band then would have to be orthogonal in field would have to be orthogonal to the lower band, which means that you will actually just achieve that by putting electric fields to overlap primarily with green, low index regions, right? And you see that these two field patterns are orthogonal. They have exactly the same periodicity in space, but you would find the dielectric band as the lowest frequency eigenstate, and then you will find the air band by minimizing functional in such a way that you also are in the eigen subspace that is orthogonal to the space of the electric band, right? So that has to be actually electric field overlapping with low index region. Does this make sense? So what is happening now, you remember there is another band here, right? At even higher frequency. How would the electric field for that look like? What do you think? I mean, periodicity has to be the same, right? All of these are block states with k equal to pi over a. So periodicity has to be 2a, right? But how would the electric field be different then? Can you do anything better than this in terms of localizing electric field in high index region? Not really, right? But what can you change? If you go back to this expression, you can change numerator, right? So if you still have periodicity of 2a, but you start increasing number of oscillations in electric field, you can make this larger, okay? So if you go to higher order bands, you will see that what happens is you still have this envelope of 2a, but you may see kind of having two lobes of electric field per high index region, right? So it's not just like a single lobe, but there are two lobes, right? And likewise for the air bands. So as you are going to higher and higher bands, you will start seeing more and more oscillations in the electric field. And of course, you know, we're not really here solving for the electric field distribution. We're just discussing what you expect to see from the bands, right? But indeed, if you actually solve for electric field numerically, this is what you will see. And we will see how that looks for two-dimensional photonic crystals in a moment. Any questions?
Question on the plot C and D. In the plot, it seems to me is continuous, but I think it should be a discontinuity between boundary and boundary if you just plot the 1/2 epsilon E squared.
In this particular case, it is assumed that the electric field only has a tangential component. If that's what you were confused about, so tangential component stays preserved, right? I mean, you are right that that's the case depending on what components of electric field you have.
Sorry, my question is the
Oh, for epsilon. Oh, yeah. I mean, this is. I thought you were talking about the electric field at the interface for the dielectric band. Yeah. So. Yeah, you are right, because epsilon, I mean, this is just a cartoon, right? Just to kind of illustrate what is going on. But you are right that depending on epsilon is different in this and this region. And if E is continuous and you have only one E field component, then epsilon E squared would be different in two regions. You're right, but this is not the actual solution, right? This is just a drawing that we're using to kind of illustrate how the field distribution would look like. This is from Giannopoulos' textbook. And, you know, as you can see, this is just a sinusoid. And it's assumed that periodic part would just be a constant in this case, which is also not true, even for lowest order block state. And, you know, if you look at the block state, it's also not just one electric field component, but, you know, kind of just illustrating sort of how electric field distribution, kind of energy density would look for these modes. Okay. Yeah. So don't take it literally, right? Yeah. Yeah, we'll see actual field distributions in a moment, numerically calculated ones for two-dimensional photonic crystals. So we can discuss it there. Okay, so before we move to that, I just wanted to say a few words about off-axis propagation. So far, everything that we analyzed was just propagation in the direction perpendicular to mirrors or to layers of the one-dimensional photonic crystal. So there was only all the block states had the plane wave, which was just e to the I k times z, in the z direction, and z axis is perpendicular to mirrors. And then there was a periodic function in the direction z, right? But in real case, of course, if you build this distributive Bragg reflector, there are situations where you will not really shine light necessarily along the z-axis. You can also shine light at an angle, theta, as shown here, which is off this z-axis. So the question is, what is going on there, right? I mean, because all the band diagrams that we plotted assume that there is only z coordinate and there are no other coordinates in the world. Well, then in that case, it's also important to see what happens for the off-axis propagation. And this will also highlight the limitations of one-dimensional mirrors, right? Because if you go back to the band diagram that we plotted and you look at this, you will say, well, this is perfect. I have a photonic band gap here, and no matter what I do, I mean, I can always use this to perfectly confine light at frequency omega, not right inside of the band gap. But that's not always the case, because this is just drawn for the propagation in the direction perpendicular to mirrors, which is z-axis. Right? If you look at this in real life and you just take that mirror and take frequency omega naught, which is inside of the band gap for what we plotted before, but you shine the wave with frequency omega naught under an angle that is very large, what would happen is that you will not really necessarily reflect light completely. And that is the reason why people actually go to additional effort to build two-dimensional or three-dimensional photonic crystals, because you cannot really perfectly confine light with one-dimensional photonic crystals. There is a finite angle for which this works. It doesn't really work for arbitrary angles. And that's also, when you localize light, when you take mirror like this and another mirror like that, it would confine well for z direction, but any confined field would also have components, k-vector components in other directions, which means that those may not be necessarily well confined, and they would leak through mirrors and limit the quality factor of the resonator and so on. So to see what happens for off-axis propagation, I mean, you basically have to solve the problem by including also additional axes, right? So what we solved previously were just by assuming that you have only z direction, right? Then everything is infinite in the xy plane, right, in plane of the mirrors, and there is nothing other than on-axis propagation in the z direction. So that's how you ended up with the block states, which were just like u of z times e to the I k z, right, propagating along the z-axis, and we wrote master equation for just z direction and all of that business that we did over the past couple of lectures. But if you have off-axis propagation, that block states would also potentially have plane wave components in the x and y direction, right? So that would be basically u of z times e to the I k z z, and then you also have plane wave in the xy plane, which may have some k vector kx and k vector ky. In the xy plane, which is the plane of each of the layers of mirrors, there is no periodicity of the structure. Right? So you just have plane waves. There is nothing that would actually discretize the eigenstates of the system or introduce any periodicity. It's just kind of free space. Everything is uniform. So to solve this problem, you will actually have to look at it as product of block states in the z direction and plane waves in the xy direction. And when you do that, and when you solve the problem, I mean, you will actually, as we'll see in a moment, come up with different possible solutions for frequencies and wave vectors. And now wave vector can have even three components, kx, ky, and kz, not just kz for on-axis propagation as what we plotted previously. And before we plot the band diagram, let's just briefly summarize, and we did that at one of the very first lectures when we looked into the total internal reflection. Now when you have off-axis propagation, it is important how your electric field is polarized. For on-axis, for z-axis propagation, right? If your propagation vector is in the z direction, kz, your electric field has to be perpendicular to the direction of propagation. So it could be in the x direction or y direction or any combination of x and y, but it doesn't matter. No matter which direction you pick, it's all the same. It would always hit the interfaces in the same way, right? Because the electric field is parallel to the interfaces. But now for the off-axis propagation, let's say your k vector is under an angle theta I relative to the z-axis, right? Like here, now it matters how electric field is polarized, right? If you have S polarization, where electric field is perpendicular to the screen, okay? Or in scientific terms, for the S polarization, electric field polarization is perpendicular to the plane of propagation. And plane of propagation is defined by the z-axis and k vector, right? So that's for us xz plane, which means electric field would be in the y direction, right? For the S polarization, electric field would hit the interface so that it's parallel to the interface itself, right? But for the other polarization, which is called P polarization, electric field is in the plane of propagation, right? So electric field always has to be perpendicular to the k vector, but if it's in the plane of propagation, that means that it would be in the xz plane, as shown with this dashed line, right? So for P polarization, clearly, electric field would not be parallel to the interface when it hits it. And from boundary conditions, it's clear that these two don't necessarily behave the same. They won't have the same frequencies, wave vectors, combinations, the same reflections, and you actually know that even for a single plane interface from the Fresnel coefficients, right? But now it's a little bit more complicated because you have multi-layer structure. So again, going back to this, S polarization means electric field polarization, of course, perpendicular to k vector, but also perpendicular to plane of propagation. P polarization, electric field perpendicular to k vector and in plane of propagation, right? So these two are not necessarily the same, right? And when you calculate the band diagram, this is what you would see for one specific example, right? So this is now different from the band diagram that we plotted before because there are additional k vector components. So if you look at this problem, right, there is certainly kz because you're launching the wave in the z direction, but the k vector can also have kx and ky component. Just for simplicity, let's assume that we only have kx. So we orient the axis in such a way that x-axis is aligned and there is a kx component, but no ky component, right? And that you can do without loss of generality because in the xy plane, everything is uniform, right? So you can just pick the wave that has kx and kz. Okay, but then that still means that you have kx and kz, right? So if you are plotting a band diagram, it's not omega versus kz anymore. It's omega versus kx and kz. So there would be basically three-dimensional band diagram. Let me just sketch this very, very briefly. Oops. I have to stop sharing here and go on my whiteboard for a moment. So right now, band diagram, well, the one that we did before was omega versus kz, right? For on-axis propagation, if you don't have kx. But now you also have potentially kx. So omega versus kz would be this. Pi over a. And so on, okay? Right? So that's what we did during the last few lectures, right? So that's just propagation along the axis. But now there is also kx, right? So now the band diagram looks a little bit more complicated if we have some three-dimensional surfaces, right? And that's kind of difficult for me to draw. I only know the cross section between omega and kz plane, but you know, in the kx direction, there would be some sort of surfaces that emerge, right? And same thing for the other direction. So we're not really drawing that. I mean, it's kind of hard to do it by hand, but what it was drawn on the slide that I will go back to is the projection of this whole diagram onto the omega kx plane, okay? So what is a projection? Projection means that you just plot everything that you have away from the omega kx plane and project all the points onto the omega kx plane, okay? So let's just go back to that. Stop sharing and start sharing this. Sorry. So here it is, right? So in this plot, what we see is a projection of that three-dimensional band diagram onto the omega kx plane. And the right-hand side is for the S polarization. The left-hand side is for the P polarization. They're clearly very different, right? And these shaded regions means that in three-dimensional band diagram, there are some sort of surfaces at those frequencies. You will hit, as you go at that frequency deeper into the three-dimensional space, you will hit some point along that surface, right? So what is this telling you? This is telling you that there are these surfaces, you know, for example, for the S polarization that are, you know, somewhere for this particular frequency and this particular Kx value, there will be some sort of Kz value where you will have some point, right, of the band diagram, and it would correspond to this block state that has both Kx and Kz component. And this solid line that we plot here and here is the light line. That line is basically just omega equal to C times Kx. Okay, this is a dispersion that a photon coming from free space would have if it only had Kx component. Okay, so why do we plot this line, right? If you shine a light anywhere from free space onto this structure, right? Where would that omega k or that particular wave have to be on this band diagram? Right? Or this is light line, this is omega equal to CKX, but if you shine something onto the structure from free space, it can potentially have also KY and KZ, right? What do you know about KX, KY, and KZ for a propagating wave incident on the structure from free space? They're all real, right? And you also know that omega over C squared would be KX squared plus KY squared plus KZ squared, okay? So omega for that wave would have to be above this light line, okay? It has to be at least on the line or above it, because omega over C squared is this KX squared plus squares of KY and KZ, which are also non-zero and positive, right? Non-negative. So anything incident on the structure, any wave incident on the structure from free space would have to be above this line, okay? Which means that if there are regions above this line where for a particular frequency until the light line, you have no gray points, then you would reflect them back. And this is the case for this particular structure, right? For example, here at that frequency, all the way to the light line, there are no eigenstates that you can couple to, which means that literally for any orientation of the incident angle here, at this particular frequency, you would reflect back into free space. And this is what people call omnidirectional reflector. It's from an old paper that Shang-Hui Fan co-authored actually, that I copied this from. But don't take this for granted, because if you take a regular DBR and calculate this, you will not really have these regions of omnidirectional reflection. This is calculated for a very exotic choice of dielectric constants, because in order to achieve this white region all the way to the light line, you have to really pick some very high contrast refractive index regions, and it doesn't really work for any DBR, right? So if you took a regular DBR that you would use for laser, or you know that you would normally use in your photonics, you wouldn't really achieve this. You wouldn't reflect light back for any angle of incidence, which means that for some steep angles of incidence, you will start coupling to the structure and propagating. So it doesn't really work as a really good mirror. Nevertheless, you know, people have used this omnidirectional reflection a lot, you know, even in so-called onion type fibers. This is from the work of Joel Fink at MIT. They made these onion fibers by depositing layers, and they actually couldn't really find the right materials to make them for telecommunication wavelengths, but they made them for longer IR. And here it's important to have omnidirectional reflection, because in the air gap that's inside, you know, you want to make sure that this structure reflects for as many angles as possible so that you can confine light efficiently. And they did it, but at the wavelengths of few microns. Yes, and it's very useful for sensing at some mid-IR wavelengths. Okay, so that's on the omnidirectional reflection and on the variational theorem. Now we'll make a 5-minute break, and after we come back, we will actually go back to two-dimensional photonic crystals and look at the Brillouin zone for two-dimensional photonic crystals, and light line and dielectric and air bands. Okay, so let's make a 5-minute break. If you have any questions, I'm also happy.
So for the omnidirectional mirror, is that a real product, or you emphasize that it's not realistic, but from this slides you can also see people already did?
Yeah, there is a company, I think, that they started, but from what I mean, from I didn't follow completely closely, but they had the product, but the problem was operation at longer wavelengths, and it used some materials. I forgot exactly which materials, but this is not glass. I mean, they do deposition of some more exotic materials so that they have very high refractive index contrast. And I think the target was not communications; it was for sensing, right? Because there are some vibrational modes at infrared, longer infrared frequencies, and then the idea was to put some molecules inside and excite them with some longer wavelength lasers. But
for the surgery CO2 laser.
That's a little bit longer, right? I think this was not there. I mean, CO2 laser is 10 microns, but this one was something like it was not ideal wavelength range. From what I recall, it was something around 2 to 4 microns were what they could achieve, but they couldn't really go to 10 or 1.5. I mean, I'm not sure unless there were some more recent developments. They wanted to do it for 1.5 and some more useful wavelengths, but it was difficult to find materials and design it so that it worked everywhere. But there was a product, there was a company. I'm not really sure what the state of that company is. Of course, there is a whole other category of fibers. I mean, photonic crystal fibers, which took off even more. And with photonic crystal fibers, it's not one-dimensional reflector, right? You have a two-dimensional pattern. And they're typically made out of glass, but you have now the ability to completely control that pattern. And some of them have air core, and people now can design them to have particular dispersion at whatever frequency they want. So those, you can actually contact Tor Labs and say, I would like to have a photonic crystal fiber with this dispersion at this wavelength, and you can actually get it back. And the prices went down significantly. So I think photonic crystal fibers took off, but they of course have two-dimensional pattern in plate.
I also one question about the application of master equation. So from the lecture, we can see we can apply that into a layer by layer photonic crystal structure. So this kind of structure is periodic in one direction and infinite on the other two directions. I'm thinking about, could we also apply that into a grating, like an infinite long grating structure that's is periodic in one direction and not periodic in another direction?
Yeah, I mean, you can. This is coming down, because for that particular direction where you have periodicity, you can still write Fourier series expansion of epsilon, right? Now the question probably that you have is, how do you handle the remaining direction, right? And in the remaining direction, you remember you have, I mean, when we wrote the most general form, we expanded the electric field in all three dimensions in space with the Fourier components, right? I mean, you can actually write Fourier expansion of electric field in the directions in which you have periodicity of the electric constant, and in the remaining direction, if you already know how your field looks like. I mean, let's say it's like some confined into some fundamental mode, like it's guided, right? You don't really need to Fourier transform into plane waves in that particular direction, right? So when you go back, so you reduce it to, I mean, if it's grading, again, it's one-dimensional periodicity, it would go back down to one-dimensional periodic structure. But the question is, how do you keep track of like other dimensions? And you can actually still look into the field confinement with a particular pattern in those directions. But, of course, real world is three-dimensional. You need to construct the equation. If the structure is has one-dimensional periodicity, you still use kind of one-dimensional form of the master equation.
So do we get any benefits if we decompose into different k vector along that periodic axis?
around periodic axis, I mean, depends on what you want to do, right? And we will do later on when we talk about, you know, what we call micropillar cavities that basically are corresponding to what you're talking about, which is you have one-dimensional distributed Bragg reflector, but it has finite extent in the other 2 dimensions, okay? That's basically what you're talking about, right? It turns out there are methods that people have developed that are pretty close to numerical methods where you can decompose that problem into kind of infinite Bragg stack, which is the problem that we solved. And that's your one-dimensional master equation. And then you also have your kind of other 2 dimensions, which lead to mode confinement. I mean, I can actually show it on this picture. Look at this, right? So it's your one-dimensional Bragg stack, but confined. And we will be solving this using that method. So it turns out that you can decompose it if you know that your electric field confinement in the XY plane is something like a Gaussian. You can calculate effective index for all the layers of the structure and reduce that to one-dimensional periodic structure problem. And then you use one-dimensional master equation problem to solve for the band gap. And then your final field would be or you use transfer matrix method. And then your final field is the product of, you know, whatever you solve from the one-dimensional periodic structure and confinement in the other 2 dimensions. It's approximation, but you will see that it's pretty close for this problem to what you would solve from numerical solution. I mean, you can obtain frequencies pretty accurately, and you can actually obtain field pattern pretty accurate. And a lot of people have done that, especially earlier on, right? I mean, now there are a lot of numerical methods, but it works pretty well.
So what kind of, so in this case, I guess my question would be a 3D grating, but
3-dimensional photonic crystal? I mean, 3-dimensional periodic, right? I think the bottom line is if it's periodic in 3 dimensions, yeah, then you go back to 3D, like the original master equation form that we introduced for like full 3D periodicity, right? You expand in 3-dimensional Fourier series for epsilon, and E field is also expanded in, I mean, we already wrote that. We just reduced it to 1-dimensional form for DBR.
Yeah.
Yeah, that's fine. That's exactly what we wrote there. But, you know, for example, if you look at the 2D here is not infinite 2D, right? You have 2-dimensional dielectric constant, but then third direction is your, you know, confinement. Let's just go back. Confinement by total internal reflection, something like this, right? So for this, you write 2-dimensional master equation, okay? But then you still need to take care of the confinement in vertical direction. And there are a few different ways of doing that. I mean, some people do this effective index, which is approximation, that confinement kind of is the same as structure without confinement, but with some lower refractive index. And then you write 2-dimensional master equation. Or you can just write field as, you know, decompose into some envelope times something which is going to end up being a block state and in the 2D plane. Yeah.
Okay, thank you.
Welcome. Yeah, I think we can now go back, right? Yeah, so now actually we'll just spend till the end of the class time discussing 2-dimensional photonic crystals and 2-dimensional photonic crystals of finite depth, like the one shown here. I mean, of course, we in real world, it's never really completely 2-dimensional, or nothing is really 1-dimensional, right? So these are 2-dimensional, meaning that you have 2-dimensional periodicity of the electric constant. But since you have to manipulate light in 3 dimensions, then what we do is we need some sort of thin wave films or high refractive index contrast slabs in order to guide light there, right? And you know, a lot of photonics is based on this thin film photonics. So how would you make something like this? I mean, you can make it in many different materials, from silicon to gallium arsenide, indium phosphide, you know, silicon carbide, whatever you like. You just need to have this guiding layer, and then you introduce on top of that this periodicity of the electric constant. And the process for this is pretty simple, and it's very similar to the way you would make any silicon photonics or any planar photonics. You do lithography, you know, then you define pattern, then you transfer that pattern through the top high index layer, which sits on low index layer. Then you remove your mask, right? You have your holes here going through high index layer. And then at that point, you already have a photonic crystal, but it has air on top and some low index material in the bottom. You can even undercut it. In this case, it would be by hydrofluoric acid. I mean, you just dip it and that hydrofluoric acid would eat away silicon dioxide underneath. And that way you end up with these suspended structures. But this is if you would like to have full symmetry, which sometimes you want for the reasons that we'll explain later. But you can also have it sit on the low index material, and that would also be a photonic crystal, although it would mix some modes. You don't have vertical symmetry. So that's a planar photonic crystal, and we already showed these pictures before. We showed these band diagrams, but we didn't explain them. Today, the idea is to explain where this band diagram comes from, and learn more about the states and this solid line, where is that coming from, and so on. But of course, everywhere in the plane, you have this distributed Bragg reflection because you have two-dimensional periodicity, and vertically you'll have total internal reflection here, right? So their states are still three-dimensional, but they are two-dimensional. Although the structure is three-dimensional, the eigenmodes would be two-dimensional block states, what we were just discussing with Yeshua, because the dimensionality of that comes from the periodicity of the dielectric constant, right? So when you plot this band diagram for the structure, on the horizontal axis, you will have in-plane K vector, right? You just plot the K vector in the plane where you have epsilon periodic. So for us, that would be this XY plane or KX-KY plane. And these are different points, which we will calculate in a moment. And on the vertical axis, you have some frequency or normalized frequency. And we'll see that this solid line here is actually a light line. It's the same thing as the light line omega equal to C times K that we plotted for omnidirectional reflector, but we'll see why it looks a little bit strange here. And still every point here on this diagram, every circle here, which is numerically calculated, would correspond to a block state. But again, two-dimensional block state. And band gap would be this region under the light line where we don't have any frequencies. And same again as for one-dimensional periodic crystal, states under the band gap and right above the band gap would actually concentrate electric field energy density in high or low index regions respectively. So for photonic crystal, low index region here is air, high index region is in this case silicon, right? So you expect, if you look at a particular K point of the band diagram, like this X point here, which we'll see what that means, but let's say look at that X point, you're expecting your electric field here and here to be represented by block states that have the same symmetry and the same periodicity, but the one with lower frequency would tend to concentrate electric field in silicon, while the one above would tend to concentrate the electric field in air. And if you look at these patterns, they kind of look like that, right? This one is translated version of this field pattern here, where electric field really lines up with holes, and here electric field lines up with regions between holes, right? So it's exactly the way our variational theorem tells us. And if you go to these even higher order modes at the same K point, what do you expect? What do you think? So these ones clearly have periodicity, which is equal to a half root 3 times 2, so it's a root 3, just from geometry, right? From red to red, I have a root 3 for both of these, right? From red to red or from blue to blue. What would be different if you go to even higher frequency in a field pattern? What do you think? Would periodicity be also a root 3 in that direction?
It'd be smaller than that. It'd be like half that.
If I pick K, this K, periodicity has to be the same, right? Because that's the periodicity of the block state. But there are different ways of arranging electric field and still having the same periodicity. Although periodicity would be a root 3, you may have more oscillations of the field in between. And that would make numerator, which is curl of E magnitude squared, larger. Okay? And indeed, as you go to higher and higher bands, there'll be more and more oscillations of the field. Does that make sense? Right? Okay. So now let's explain what these gamma and X and J mean, right? Where do they come from? And, again, as we said before, we only need block states inside of the first Brillouin zone, or for irreducible first Brillouin zone, which was 0 to pi over a, 0 pi over a for one-dimensional structures, but that irreducible first Brillouin zone is this triangle for this hexagonal lattice photonic crystal. So where does that come from, right? Let's solve for that, right? Okay, so you may have seen something like this before, but if you haven't, it's exactly the same as what we did before, right? I mean, it's just based on the expressions that we already introduced. We just need to do a little bit of geometry to find the first Brillouin zone. So going back to hexagonal lattice, this hexagonal lattice has two, well, primitive lattice vectors, A1 and A2, right? Why are these primitive lattice vectors? When you are looking for primitive lattice vectors, you have to find two vectors so that any point inside of the lattice can be described as a superposition of these two vectors, okay? So what is the unit cell? Unit cell would be this parallelogram here, okay? If you pick any other unit cell, if you say, well, my unit cell is a triangle, right? Equilateral triangle, that's not a unit cell because you cannot tile a lattice with this triangle. You would have to flip it upside down afterwards. Unit cell, yeah.
So on the previous slides, are we, you talk about many dots and you say each dot is the Bloch state.
Yes.
I'm wondering, is that just a numerical result that you only have finite amount of them where you have a continuous?
That you have finite amount of band where you have continuous what?
Where you have a continuous line where just
yeah, this is a numerical result because this is calculated numerically using finite difference time domain methods. So you basically, the way this is calculated is slice by slice in K space. You pick K vector, right? You pick unit cell, you excite all the possible frequencies and you do Fourier transform to find peaks, right? But K is constrained. And then you change K vector, and depending on what discretization you use for K, that would basically imply the step size in the K direction. So in this case, I use 12 points per each direction, which is why you see this step, right? But these are complicated things. So if you, I mean, you have to do it numerically, and you cannot really solve for the band diagram of this analytically. I mean, you can approximately find band gap, but you cannot really solve it analytically. Okay, so now going back to real space. So this is real space lattice. You know, I drew some pillars with the electric constant epsilon 2, you know, in free space on a hexagonal lattice. People call it hexagonal or triangular. I mean, because Brillouin zone is hexagon, but you know, this nearest neighbors form triangle. So I'll call it hexagonal. If you actually look at the primitive lattice vectors, there are A1 and A2 separated by 60 degrees, and unit cell is this parallelogram. And you can see that, you know, when you're building up the lattice, the only operation that's allowed is translation. There is no mirror or anything like that. So it's clear that this parallelogram is a unit cell because I can build up the whole lattice just by translation. And any point inside of the lattice can be obtained by combining A1 and A2. Does that make sense? Okay, so this is your unit cell, right? And A1 and A2, they have exactly the same length, right? The length would be A, separation between different nearest neighbors in the lattice. But I can also express that A1, I mean, I can align up real space X direction with A1. So then A1 is A times unit vector in the X direction. And A2, I mean, I can actually project it onto X and Y axis. A2 would be A half times X plus A half root 3 Y, right? Because this is 60 degrees, okay? So now how do we find the reciprocal lattice? The only thing that we need to find reciprocal lattice is to look at the relation that we introduced previously. We have to find two primitive vectors, reciprocal lattice vectors, B1 and B2 in such a way that dot product between those vectors B and vectors A gives you 2 pi Kronecker delta, right? So then you have to find B1 and B2 so that this is satisfied, okay? So that means that I will pick B1 vector in such a way that it's orthogonal to A2, okay? Do you see my pointer here? Or do you see my pointer on the screen? Okay, so B1 is orthogonal to A2, and I will pick B2 that is so that it's orthogonal to A1, right? So I'll pick a B2 along the y-axis, or actually ky axis, because I introduced kx and ky so that they are lined up with x and y, but x and y describe real space and kx and ky describe reciprocal space, right? So B2 would be along ky, and then B1 would be somewhere here, orthogonal to A2. Of course, the choice of these two is not unique. I mean, you can say, well, I can also pick B2 so that it goes down, or I can actually pick my B1 so that it goes here. It doesn't matter. All of these would give you the same result as long as you satisfy these relations. Does that make sense? Okay. And if you do that, if you just write that, I mean, you already know directions are constrained. It's very simple trigonometry because this is 60 degrees angle, right? If I pick B2 so that it goes here along the ky axis, it's orthogonal to A1, and inner product with A2 would be product of their lengths times cosine of 30 degrees that you have in between. So you have to play a little bit with trigonometry, but it's very simple to show. And you know, you'll do something similar in your homework as an exercise, right? But it's very easy to show that basically B1, which is orthogonal to A2, I picked it to go over here. B1 is given here, and B2 is just along the y-axis or ky axis, and it would have the length of 4 pi divided by root 3a. Okay, you can prove that from trigonometry, right? So B1 goes here, B2 goes here, or here is another picture zooming in on them. B1 goes here, B2 goes here. Both of them have the same length, which is 4 pi over root 3a, right? So of course it's inversely proportional to length, except that one goes along this direction, which is orthogonal to A2, and the other one goes along the y or ky direction, okay? So if you look at them as this, the angle between B1 and B2 is 120 degrees, and they have the same length, which means that they also form this parallelogram or rhombus, right? Which is having the length of 4 pi over root 3a. And reciprocal lattice is the lattice defined by these two reciprocal lattice vectors. So what would be the reciprocal lattice here? What type of the lattice would it be? I have two vectors of equal length, which are separated by 120 degrees, right? They define a parallelogram. If I slide this parallelogram in space, what lattice do I describe? Is it a rectangular lattice? No, it's the same type of lattice, triangular lattice, right? Except that it's rotated by 30 degrees relative to the original one, right? And of course, it has inverse lengths. It doesn't have actual length. So for this one, nearest neighbors would be, you know, along this direction, 0 and 60 degrees direction. For this one, it would be 30 and 90 degrees. You see that, right? So it's a rotated triangular lattice. Okay. Does that make sense? So now the next step is we need to find first Brillouin zone. How do we find first Brillouin zone? Once you have a reciprocal lattice, what do you have to do? You remember the rule?
Draw the bisectors of the lines.
Exactly. So you have your reciprocal lattice. Now you have to plot perpendicular bisectors to all the nearest neighbors. So let's pick one node and plot the bisectors, right? So it would have 6 nearest neighbors. Here is a bisector, another one, another one, another one, another one, another one. So first Brillouin zone is a hexagon. Okay? And then you can show by symmetry that each triangle in this hexagon is exactly the same, right? Because there are 6 equilateral triangles. And moreover, you can show that there is a symmetry relative to positive and negative kx, the same thing as for one-dimensional lattice. So it's enough to even have half of the equilateral triangle. And we typically pick this particular half. Gamma is always corresponding, capital gamma is always corresponding to kx, ky equal to 0. And then there would be x point here. Although sometimes people actually use different letters, but we will label this one as X, and then J, or sometimes labeled as M, would correspond to this diagonal direction. Okay, so these are the edges of the irreducible first Brillouin zone. And I know that if I have all the block states inside of this little green triangle, I have all the block states of the system. And moreover, if I have block states along the edges of this irreducible first Brillouin zone, I will have sufficient information to find the size of the band gap, right? Which is why when you look at the band diagram, we just plot it along the edges, gamma x, xj, gamma j, right? I didn't plot it for all the points inside of the triangle, just the edges of the triangle. That's enough for the photonic band gap. Okay? So we plotted gamma x, xj, gamma j, right? So going back to the band diagram, that's gamma x, xj, and gamma j, okay? So what are these directions, gamma x, xj, and gamma j, right? I have exactly, I mean, I know B1 and B2, they have length of 4 pi over root 3a. I mean, this is 90 degrees, this is minus 30 degrees. It's very easy to find what these are, right? I mean, for example, gamma x, obviously, I can already tell what it is. It's along the ky direction, right? So going from gamma to x means that kx is 0, ky goes from 0 to 2 pi over 3a, root 3a, right? Because I know that the length of the reciprocal lattice vector B2 is 4 pi over root 3a, but I go only half to it because you are plotting perpendicular bisectors. Is that okay, right? So then for gamma j, I mean, it's 30 degrees relative to that. I have to change both kx and ky, but you're changing them in such a way that the angle between kx and ky is 60 degrees, right? So they satisfy tangent of 60 degrees relation between the two of them. You're not changing them arbitrarily as you're going from gamma to j. And then as you're going from x to j, what is your kx and ky? Maybe someone else can say. What is ky?
2 pi over root 3a.
Exactly. And then kx is changing between 0 and whatever value it has at the j point, which we'll write now. Exactly. So now, I mean, this is the final result, right? Gamma x direction, as you said, kx is 0, ky goes from 0 to 2 pi over root 3a. Xj direction, ky is 2 pi over root 3a, kx changes between 0 and 2 pi over 3a. I mean, this is just coming from the value at the j point. You can easily calculate that one. And then gamma j direction, kx goes between 0 and 2 pi over 3a, like here, but ky is root 3 times kx. And that comes from the fact that the angle is 60 degrees between kx and ky. Everybody okay? Okay. So then, now my question for you is, why does the light line look like this, right? Light line would be what? Light line for this plot would be defined in what way? Light line for 1D was omega equal to c times kx, right? But now I have on the horizontal axis kx and ky, right? So the total value of the k vector would be kx squared plus ky squared, right? Of course, wave can have only also kz, but here I'm plotting only two-dimensional k vector. So on the light line, I'm plotting the dispersion diagram for a free space photon that only has kx and ky, okay? So for light line, I'm plotting omega divided by c squared is equal to kx squared plus ky squared. And then if a wave is incident on the photonic crystal from the outside, let's say this is a photonic crystal and a wave is incident from the outside, it could also have real kz, but it would have to be above that line because it would have kx squared plus ky squared plus kz squared, and kz squared would be greater and equal 0, right? Which means that the frequency of that wave has to be above this, okay? But why is the light line kind of broken like this? Any thoughts?
Because we like step around like the Brillouin zone. So like in the first part from gamma to x, we only change kx.
Exactly.
And then the x to j, it's only ky, and then from j to gamma again, it's both kx and ky change.
Exactly. So from gamma to x, you change only one, so it's linear. From gamma to j, you change both of them, but they're related by a multiplicative constant. So it's kind of like linear again. And then here, one of them is constant and the other one is changing. So you will have that omega is c times square root of constant times square of kx, okay? Which is why it looks like this. And then anything that's incident on the structure from free space would have to be on the light line or outside of it. Every point in this Venn diagram is a block state, two-dimensional block state that would look like this. Okay, right? And then these kx and ky in the block state would be whatever you read from here. So now going back to this particular point, x point of the Venn diagram, you remember what x point was? Kx was 0, ky was 2 pi over root 3a, right? Okay, and that ky direction, if you actually go back to how we defined it, was the direction in the real space lattice that was kind of going from the bottom of the equilateral triangle to the top of the equilateral triangle. Okay, we can actually go back to see how that lines up, right? So here is our y direction. It goes from the bottom of equilateral triangle towards top along the height of the equilateral triangle, right? That's your ky direction, because a reciprocal space lattice is rotated by 30 degrees. So if you're looking at the ky direction in real space, it would be along the heights of these triangles, right? How many different gamma x directions are there? I mean, they're basically 6 different ones, but this one here and this one here are the same, right? But I could actually look at it, propagation in this direction or in any direction where you go along the heights of the triangles. They're completely equivalent, right? So here we plotted it. I mean, I know that gamma x direction is kind of propagation along the height of the triangle. So this would be propagation in this direction, right? And indeed, this wave propagates in that direction. And at the x point, you expect its periodicity to be what, right? So the x point is 2 pi over root 3a, right? So you expect the periodicity to be 2 pi divided by 2 pi, 2 pi divided by k, which is just root 3a, right? And if you look at this, the periodicity from red to red is exactly 2 heights of the triangle, right? Which is 2 times a half times root 3, and that's root 3a. Do you see that? Same for this one here. From here to here, it's root 3a distance, right? So even if you didn't calculate, if I didn't tell you that this was x point, if you knew that x point of the Venn diagram, what x point of the Venn diagram is, which is kx is 0 and ky is 2 pi over root 3a, you would know, and you know that gamma x direction kind of cuts along the heights of the triangle, you would know that these patterns would both have to be for the x point of the Venn diagram, right? Based on the periodicity of the pattern. So if you know what different directions correspond to, you can kind of guess which point of the Venn diagram they correspond to. And moreover, you would exactly know that this one is dielectric and this one is airband, because this one has field that overlaps with high index and this one has field that overlaps with low index. So even if I didn't tell you, you would know that this one has lower frequency than this one. Does that make sense? Okay, so we'll do more of this exercise. I mean, next time I will wrap this up. Before we move on to coupled mode theory. I'm already at the end of the class today, but you will also have some homeworks where you will calculate the first Brillouin zone and look at the different directions, and that will help you develop intuition, right, for how states are supposed to look like. Any questions? Okay, if not, I'll see you folks on Tuesday. Bye-bye, have a good weekend, see you.